All right, so the laws of thermodynamics. Yesterday we introduced this term, okay, thermodynamics. And thermodynamics talks about the movement of energy, okay, specifically thermal energy, right? But it talks a little bit about mechanical energy as well. But basically, thermodynamics means changing thermal energy. Dynamic means changing, okay? Thermal means heat, all right? So this is changing levels of heat, essentially being converted to other forms or being transferred from one place to another, all right? So all machines are governed by the laws of physics, okay? You can't break the laws of physics, all right? Scotty told Kirk that all the time in the original Star Trek, okay? Whenever Kirk wanted more power, Scotty would always tell him, you cannot break the laws of physics, okay? Well, you can't, right? You can get around them maybe, but you can't break them, all right? So those laws describe the relationships between work and energy transformations. If we want to get mechanical work done, we've got to find a way to get the energy in order to do that. All right, so the previous sections we talked about how energy transformations or transfers resulted in changes in motion or position of an object. Okay? This section is going to deal with changes in temperature that are also the result of work, okay, and energy transformation. So essentially, anytime something moves, we're probably going to generate heat in the real world because there's always going to be friction and wear and things like that. Okay, one of the first things we got to talk about is this important term, systems. All right? A system is basically a bunch of things that are interconnected or interacting at any point in time. All right? So if I had, let's say, a bucket strung over a pulley on a rope going down into a well, okay? Myself, the rope, the pulley, and the bucket are all part of a system because a change in any one of those things will result in a change in the others. Everyone kind of follow me there? Okay? If I pull on the rope, I'm doing work. I'm transferring energy to not only the surroundings, but also the rope, the bucket, possibly the water, if the bucket was in the water, the pulley, all of that stuff. All of that is going to have a change in energy as a result of the change I made. All right? So any set of interconnected parts, okay, is a system. Now, there's different kinds of systems. Okay? So, in studies of energy transfers, a system is the object or objects involved in the transfers. Okay? Everything else is considered the surroundings. Okay? So, the surroundings are the environment. Okay? So, for us, our surroundings would be the air in this room, okay, and things like that. Okay, so this example that they have a gasoline-powered lawnmower. Okay, the system would be the engine. The surroundings could be the other parts of the mower, so the blade, the wheels, okay, and the air, the ground, etc., that are around the mower. Because as the engine runs, it's going to change the speed of the blade. Okay, and that's the engine running is going to transfer heat to the ground, to the air, and all of those kind of things. So the surroundings get energy from the system. Did everyone follow me there? Okay. All right, so the three kinds of systems. Open systems. Open systems can exchange matter and energy with the surroundings. Right? So we are an open system. Okay? I'm an open system because I exchange matter and energy with my surroundings. Right now, I'm exchanging matter with the surroundings because I'm breathing in and out. All right, as I breathe in and out, I'm taking oxygen in, I'm breathing carbon dioxide out, the air is moving in and out of me, I'm exchanging matter with the surroundings. Okay, my body temperature is 37 degrees Celsius, the room's temperature is 21. Okay, if there's all of us in here, will the temperature of this room go up? Yes, it will, always does. Okay, every day after you guys leave, it's about 2 degrees warmer in here. All right, you get 37 degrees Celsius bodies in a room, the temperature of the room will go up. All right, because we're an open system and we're exchanging energy with our surroundings. Okay, if it's a really hot day, like it's 42 degrees outside, how do you feel? Hot, because now your surroundings are hotter than you, and now they're transferring energy to you, and that's unpleasant. Okay, because it's very difficult to cool yourself off when your surroundings are warmer than you are. Okay, everyone follow me there? The closer your surroundings get to your body temperature, the more uncomfortable you are going to be. Right? Because you're going to have difficulty transferring energy away from your own body and keeping cool. All right. A closed system cannot exchange matter, but can exchange energy. with its surroundings. So let's say you went to the grocery store and you bought a bunch of steaks. Okay? And well, obviously you can't eat them all, so you threw a few of them in Ziploc bags and threw them in the freezer. Okay? The Ziploc bag is a closed system. The steak can't get out. Okay? Nothing inside the bag can get out because it's sealed. It's airtight. All right? So there's no exchange of material between the inside of the Ziploc bag and the freezer. However, what happens to the steak? It freezes. Does that mean it exchanged energy with its surroundings? It sure did, because it wasn't frozen when you put it in there. All right? So its temperature decreased because it exchanged energy with its surroundings, but didn't exchange any material. Okay? Like a thermos would be also like a closed system. It's insulated. It slowly releases energy to the surroundings, but it's sealed. Whatever's in the thermos doesn't get out. Okay? Is everyone following me there? All right. Then there's isolated systems. They can't exchange matter or energy with their surroundings. It is essentially impossible to create a perfectly isolated system. It's easy to create a closed system. You can create something that's airtight that doesn't exchange matter. But to perfectly insulate something and not allow it to make any exchange of energy with its surroundings is essentially impossible. All right? Energy is always going to be exchanged, even if it's a small amount. All right? Well, it's a theoretical construct, essentially. Okay? We have a lot of systems that are close to isolated. All right? If you had like a big cooler, right, and you had a bunch of pop in or whatever, you had a bunch of ice in there, it might stay cold for a couple of days because it does a pretty decent job of isolating the energy outside from the energy inside. It's not perfect. Okay? So we tend to say that some of our well-insulated closed systems are like isolated systems. But to make a perfectly isolated system is essentially impossible. That's why eventually all those things like those biosphere projects that they've done eventually all collapse. Okay? Because if they're always bleeding away some energy. Okay? And so they eventually just stop. Right? And that's the big problem with sending humans to distant places in space. Okay? Even to a place like Mars, which is relatively close, astronomically speaking. To send people there in terms of matter and energy is a big deal. As you get further away from the Earth, you're losing more energy to space. Where do you get that energy from? You've also got fuel and things like that. You're losing some matter to space all the time. Okay, stuff like that. So yeah, to make a perfectly isolated system is very difficult. The International Space Station is probably the closest thing we've ever done. All right? It's not a perfectly isolated system though, okay? Because the space toilet exchanges matter with the surroundings. You guys know how the space toilet works? Okay? When they sit on the toilet in there, because it's zero gravity, you can't actually sit on it, you have to be strapped to it. Okay? You think about going to the bathroom with no gravity. You kind of count on gravity when you go to the bathroom. So things fall away from you. In zero gravity, they don't fall. So they actually open this little thing that is open to the outside to space, and there's a vacuum suction that pulls stuff away. They say it's very windy when you sit on the bathroom in the International Space Station. That's how they make sure that the stuff falls away from you. It's kind of disgusting, but okay. These are things you have to consider when you're an astronaut. Okay, throwing up in space. You imagine, no gravity, you throw up everywhere. Okay, yeah, not so good. Ireland, can you open the door for Joshua there? All right, so isolated systems can't exchange matter or energy. They would be perfectly insulated. All right, so if you were, let's say, to pour coffee in a thermos that was a perfectly isolated system, it would stay hot forever because it would never exchange any of the heat with the surroundings. Okay, anyone got a perfectly isolated thermos? Okay, I mean, I've got a thermos here for my coffee, and it's usually still hot by lunch. Okay, well, by 1 o'clock, it's not. It's like tepid by then. All right, it's pretty well insulated, but it's not isolated. It's still exchanging some energy with the surroundings at all times. How can I tell that? Well, down here, it's pretty cool actually, right? The liquid inside is hot, but in the outside of this feels cool, but up here, it's warm. Okay, I know where it's leaking the energy from. Right? There's places that it's difficult to insulate. All right, so those are the three kinds of systems. Could that very easily be a multiple choice type question? Yes. Alrighty. Now, the first law of thermodynamics. Okay, first law of thermodynamics talks about the law of conservation of energy. In fact, they're essentially the same thing. Okay, energy can't be created and it can't be destroyed. Is essentially just like the law of conservation of mass. Matter can't be created, can't be destroyed. Neither can energy. You can't create it, you can't destroy it, but you can transfer it. You can convert it. Okay, you can do all kinds of things with it, but it's always going to be there. All right, everyone with me on that? It doesn't always mean it's going to be in the form you want or doing what you want. All right, so it's important to distinguish heat from work. Okay, work involves the movement of matter from one location to another. Okay, whereas heat is a transfer of thermal energy from one location to another. Possibly the most important paragraph in that section of your notes. Okay, because it distinguishes between work and heat, tells their similarities and their differences. They're both transfers of energy. They're just transfers of different kinds. Okay? Work is mechanical, heat is thermal. Okay? I can increase the energy of a system by doing two things to it. All right? Energy can't be created, it can't be destroyed, but I can increase the energy of a system by doing two things. Either I do work on it, which means I pick up the system and physically make it go faster or put it higher off the ground. Okay? Or I heat it up. Okay? Either one of those two things increases the energy of that system. Everyone follow? Similarly, I can decrease the energy of a system by doing the opposite. I can make that system do work on something else. If it does, it's going to transfer mechanical energy away. Or I can put a colder object next to it and it'll transfer thermal energy away. Okay? And that will decrease the energy of the system. But is the total energy still all there? It is. It's just not in that system anymore, but it's still here. All right? I can't create energy, I can't destroy it, but I can make it go different places. I can turn it into different things. That's the thing we got to remember. Okay? Everyone with me on that? Okay? I can turn energy into different forms, I can make it go different places, but I can't destroy it. Okay? Nor can I magically create it. I can bring it in from somewhere else, but I can't create it. All right. Now, this talks about heat flow. All right? If this person here in this picture was to heat up this metal rod, which if they were going to do that, they should probably wear gloves. Okay? But if they were going to heat up this metal rod and then they put it in a bucket of water, where does the heat go? Into the water. Because heat always flows from hot to cold. That's the second law of thermodynamics. Okay? The second law of thermodynamics talks about the direction in which heat flows. All right? Energy, in general, always goes from a high energy object to a low energy object. When we're talking about thermal energy, okay, that means from hot to cold. When we're talking about mechanical energy, we're talking about, let's say, a fast-moving object to a slow-moving object, okay, or from a highly positioned object to a lower positioned object. Okay? So that's what we're looking at here. Energy can flow out of a system to its surroundings, or work can be done by a system to its surroundings. Okay? So the first law of thermodynamics is kind of highlighted already there for you. Okay? That's important though. Okay? Is really just a restatement of the law of conservation of energy. Okay? All right. Yeah, we'll skip that part there. Okay. Perfect machine cannot be achieved. How many people have heard of a perpetual motion machine? Okay. A perpetual motion machine is supposedly a machine that can run forever with no input of energy. Okay? Why can't that happen? Why can't a machine run forever without any input of energy? Partially, but I mean, why, if I get something going, can't it just run forever? there's always resistance. Okay? There's no way to eliminate all forms of resistance. Okay? And so, anytime energy is being converted from one form to another, energy is going to be lost in that conversion. And when energy is lost, it goes from the high energy area to the low energy area. So a system is always going to be losing energy to its surroundings. Even if it's doing that at an incredibly low rate, it's still eventually going to stop. Right? There's always going to be some energy lost. The other problem with a perpetual motion machine is, even if you could make one that ran forever, that's all it would do. You'd never be able to use it to do any work. Why not? Why couldn't a perpetual motion do any work? Joshua? Right. As soon as it does work, it transferred energy away. Then it would stop. Okay? If you don't add any energy to it and it does work, it lost energy and it'll stop. Okay? So a perpetual motion machine would be nothing more than a trivial creation, even if it was possible to make one. Okay? Even if you made one, it wouldn't do anything except run. Yay. Okay? But it wouldn't do anything useful. Right? Wouldn't do any work. In order for something to do work, it's got to have more energy put into it to keep going. All right, so perfect machines or perpetual motion machines, obviously, like we say, they're not going to work, okay? Because you cannot have all of your input energy completely converted into mechanical energy. There's always going to be some energy lost in the conversion. All right, so it is the second law of thermodynamics that forbids the creation of a perpetual motion machine. Energy will always flow from high to low. All right, and that's what this is saying here. Second law states that heat, or even energy in general, naturally flows from the high energy object, in this case hot, okay, to cold, but never from cold to hot. Okay, we use this idea all the time in the creation of like electronics, okay, especially like circuit boards and things like that, because they generate heat. As the moving charges go through the circuit boards, there's resistance, okay, and that resistance generates heat. Right? When you turn on your computer, what's the first sound other than the beep that you usually hear? The fan coming on, right? Okay, the fan comes on because it needs to ventilate, it needs to constantly bring cooler air into the computer so that energy can be transferred from the electronics to the fan. If you have a very, let's say, high-powered computer, it may also have heat sinks in it. Okay, heat sinks just look kind of like big chunks of metal with kind of folds on them. Okay, and what they're made of is certain types of material that can rapidly absorb large amounts of heat. They're usually located right next to the fan, right? And that way they can absorb heat from the electronics more quickly, and the fan can ventilate the heat away. All right, so we use that idea to help keep things cool. All right, if you place a hot water bottle in your bed, don't roll over on it. That should be obvious, right? Okay, it'll warm up the bed because it's hotter than the bed. Okay, you're using the second law of thermodynamics. Okay, when you stand next to a fire and warm up, you're using the second law of thermodynamics. The fire is hotter than you are. Okay, the heat is moving from the hot area to the cooler area. All right, now these two diagrams here are pictures of perpetual motion machines that people thought would work. Okay, this one here on the left has these little balls in it, okay, and it's got these curved kind of pie slices. So as the circle would spin, the balls would roll over this hump to the edge. More of their weight would be outside, and that would push the wheel around. And then hopefully its momentum would carry it back up, in which case they would roll back towards the center as they approached the top. If you got this thing started and it started going, would you hear sound from it? Yes, that's why it would stop. What's sound? It's a form of energy, right? And if that thing is making sound, it's transferring energy away, and it's eventually going to stop. Okay? It's the same with this thing, although I think this one had a better chance, right? Because it's using a magnet. If these are made of a metallic, material like iron or steel or something like that, yes, they'll be attracted to the magnet. They might move up this thing the first time and fall through the hole, but when they come back down here, they have to open this door. And so as they roll down here, they hit this door, and the door opens, and the ball is supposed to roll over to here, where it would then be attracted by the magnet again. But if it has to open that door, what does it have to do? It's got to use energy. It's got to do work. Okay, this thing is always going to be losing energy. Okay, and eventually the ball will stop because of the resistance of this door. Okay, it's not going to work. This thing here, this ramp is not as long as this ramp. It's not going to get as much energy by going down this ramp as is used to take it up this ramp. So eventually it'll stop. Okay, and magnets don't last forever. Okay, eventually they lose their magnetism. All right, questions on that part there? Okay, so the second law of thermodynamics talks about the direction of energy flow. The first law of thermodynamics talks about energy can't be created, can't be destroyed. Okay. Typically, guys, the way you get tested on this, multiple choice. I give you a situation and I ask you which law of thermodynamics most applies in this situation. That would kind of be how that would work. Evan? There's also one called the zeroth law that we don't really talk about, but essentially those are the two important ones. Yeah. All right. So the idea of the heat engine. We talked a little bit about this yesterday. Okay. The idea of the heat engine is to harness this energy flow. If I know energy flows from hot to cold, and I put something in between, I should be able to harness that flow of energy and steal some of it on its way from hot to cold. All right, that's the idea behind the heat engine. So if I steal some of that energy, it would follow this path, which is work being done, harnessing that energy and making it do something useful. All right. Yes, still a lot of the energy is just going to go to the output area, to the low temperature area, but hopefully along the way I can catch some of it and make it do something. All right, so that's the idea behind the heat engine, is to harness the second law of thermodynamics. Okay, so a heat engine is a device that converts heat into mechanical energy. All right. Now, an internal combustion engine kind of uses this a little bit. Okay, internal combustion is the kind of engine you have in your car, unless you have an electric car. I don't think too many of us drive those here. Okay, even a hybrid car still has an internal combustion engine. All right. Now, with the internal combustion engine, here's what goes on. Okay, fuel is ignited in an internal combustion engine. Right? When that happens, it generates a lot of what? Heat. Okay. Since mostly what's in the cylinders, okay, of your engine is gas, when gas gets hot, it expands. Okay? Gases expand way more than liquids and solids do when they get hot, and when they expand in a fixed space, they exert pressure. All right? So the heat that is generated in there causes the gases to expand, which allows them to do mechanical work. That is, push the piston down in the cylinder, and that turns the crank, which powers the wheels of your car. All right? So we're using heat, and we're turning it into mechanical energy by using it to heat up gases that can expand and then as a result do mechanical work. Everyone follow me there? Now, are there a few conversions in the middle there? I mean, first there's the generation of heat, chemical energy into heat. Some energy is going to be lost there. All right? 30% of the energy used in your car is actually used to keep it from melting down. That's how much heat it generates. So not all of it's doing useful work. Okay? Then we've got the gases expanding and pushing on all sides of the cylinder. There's going to be some energy lost there. As the cylinder moves down, is there friction? Yep, energy is lost there. All right, so it's not a terribly efficient transformation of energy. It works, but it's not terribly efficient. Every time energy is converted from one form to another, some is going to be lost. Okay? What tells you how much is how efficient the machine is. All right, so the exhaust heat has a lower temperature than the input heat, and that's why a lot of the heat goes out the exhaust or into your coolant system. Okay? Running all throughout the engine block of your car is coolant, the green stuff that might, if it's leaking out of your car, that you need to get fixed right away. Okay? And it runs through there in these ducts and pipes and whatever else. Okay? And as it runs through there, it absorbs heat energy from the engine. Okay? And then it goes to the radiator, and the radiator has a fan on it, and it blows that heat into the surroundings. Okay? Removing it from the engine using, again, the second law of thermodynamics. Okay? Everyone follow me on that one? Okay. All right. Now, here's the design for the original heat engine. Okay? We had this idea that if we built this boat and we had a short pipe that was in the surface water that's warm and a long pipe that goes way, way down into the cold water below, that heat energy and water, as a result, would flow through the heat engine and then down into the cold water. It's great theoretically. Why doesn't it work in practice? Sort of. Oh, nothing to do with it being wrecked. No, nothing to do with that. No, I mean, according to the second law of thermodynamics says that this should go through here. Okay? It should move this way. Okay? But here's the problem. The water here and the water way down below aren't all that different in temperature. It's only a few degrees. If you're going to get significant flow, you've got to have a major temperature differential, and we don't really have that. The second thing is that this water and this water are already in contact with each other. Right? They don't need to go through here in order to circulate. They already circulate. So you just don't get an effective flow of water through there. A heat engine works provided there's a major temperature differential between the hot part and the cold part. Then it'll definitely flow where you want it. Okay? But in this case, there's just not a significant enough difference in temperature for it to work effectively. All right. So heat can be made to move from cold to hot if we do work. Okay? I can actually make energy go from cold to hot. But I've got to use energy in order to do it. This is kind of like active transport for heat. Okay? Is what I'm going to talk about next. Okay? So these are heat engines. The next thing is the heat pump. We may have places where we want to keep things cold, like your refrigerator, for example, or your house if you have air conditioning. If you want to keep your house cold, where do you have to pump the heat? Elsewhere. Outside. Is it already hotter outside? Okay, it's already cooler in your house than it is outside. So how do you make the heat go from where it's already cool to where it's already hot? Because it says that it should go the other way. It should come from outside to inside. All right? The only way to do that is to actively pump that heat out. And that requires you to put in energy. Okay? A pump uses energy. That's why we call it a heat pump. You can do it, but you have to put energy in. All right? We talked about how the jet engine was the example of a heat engine. Okay? When we ignite the jet fuel, it gets very, very hot. Okay? Air is drawn in through the intake. Okay? Through to the hot area, and then it wants to move from hot to cold, so it goes right through the turbines and out the back of the engine, forcing air back, forcing the plane forward, and that drives the plane. Okay? A heat pump would be like an air conditioner. Right? An air conditioner or a refrigerator is a heat pump. Okay? I'll show you how those work. Sorry, there's another example of a heat engine. This one actually works. Okay? If you can set it up. If you put an electric motor with two different leads, one in really hot water and one in really cold water, you'll actually get a flow of energy, which will become electricity and run the fan. Okay? How long will it run for? Till the water's the same temperature. It'll go slower and slower and slower and slower until the water equalizes. Okay? At which point the fan will stop running because there's no transfer of energy through anymore. All right, so a heat pump works like this. In your refrigerator, okay, there's these little tubes, okay, and they're full of the refrigerant. It used to be Freon, but they don't use that anymore because it's bad for the ozone layer. Okay, so now they've got the CFC-free refrigerant that runs through your refrigerator. It runs through these coils. Now, when it goes through the coils, there's a little thing, and this is the thing you can hear running, okay, in your refrigerator. It's called the compressor. Okay, what it does is it takes the gas that's in these coils and it puts it under pressure. And when it puts it under pressure, it can turn it back into a liquid. But when it does that, what does it give off? Heat. Okay? That's why if you stand next to the fridge while it's running, you feel hot air coming out from underneath it. Okay? The hot air coming out from underneath it is the energy that this coolant has absorbed from your food as it travels through the refrigerator. Okay? So your food transfers heat to the coolant, and the coolant changes from a liquid to a gas. Then the gas goes down to the compressor, and the compressor forces it back into a liquid form, and the heat comes out. Okay? All the heat that it absorbed in changing state from liquid to gas comes out, and the fan blows that heat into the surroundings. Okay? Are the surroundings warmer than the inside of the fridge? Yeah. We're forcing heat to go the wrong way, but we got to use a lot of energy in order to do it. Okay? Your refrigerator is the single largest consumer of electricity in your home. unless you have an electric hot water tank, and then that will be the biggest one. Okay, but your refrigerator uses a lot of electricity because it's breaking, not so much breaking, getting around the laws of physics, okay, by pumping heat the wrong way. An air conditioner works exactly the same. Okay, the air from your house comes into the air conditioner, and inside the air conditioner are a whole bunch of these coils. Okay, and the air from inside your house transfers energy to the coils. Okay, the coils, the liquid in the coils changes to a gas. The gas gets compressed and turned back into liquid, and the fan blows that outside. Mm-hmm. No, if you just have a fan with no air conditioner, it's going to blow it's going to try and blow the air from inside out. But if it only blew air out, eventually you create a vacuum inside and everyone would die, right? So air has to come in from somewhere to replace that air that's being blown out, and where's it coming from? Outside. So if all you run is a fan, the only thing you're going to get is the benefit of moving air going by you to evaporate your sweat, which makes you feel cooler, but it doesn't really make you cooler, right? So yeah, just having a fan doesn't do a whole lot, okay? But having this compressor that can absorb energy because of the refrigerant, that can transfer energy away and make the inside cooler. Yes. All right, so does that make sense? Okay, but we have to use energy. A heat pump is like active transport for heat. We got to use energy to move it the wrong way. Okay, heat engines use the law of thermodynamics. They're like diffusion. Okay, they just allow it to go the way it would have normally gone. Alrighty, so you got some check and reflect questions here that I want you to answer. All right, and in fact, I want you to answer all of them. Okay, all of these questions here. Okay, because I've actually asked questions like this on the written portion of this exam in the past. Okay, so I'll give you a few minutes on those and then we'll go over them together. All right, let's talk about these questions here, guys. So first off, we want to define the term thermodynamics. What is thermodynamics? Right. Okay. Changing of heat or moving of heat. Okay. From one object to another, system to another. Okay. Essentially what we're doing there. Okay. First law of thermodynamics. What does that say? What does it say about energy? All right, Evan.
Energy cannot be destroyed or created.
Right. Okay. It's the law of conservation of energy. Energy can't be created. It can't be destroyed. Okay. Difference between work and heat, and this is probably one of the most important things, okay, that we need to understand in this unit. Okay, work and heat are both transfers of energy. It's the kind of energy they transfer that's different. Okay, work transfers mechanical energy, so we're talking about movement of physical objects. Okay, heat is a transfer of thermal energy. All right, so we're not talking about necessarily the movement of physical objects anymore, just a transfer of thermal energy. Okay, identify whether each of the following is best explained by the first law or the second law of thermodynamics. Why does a bouncing ball eventually stop bouncing and come to rest on the floor? Ken? Okay, it's making a sound, okay, and that sound is a form of energy, so it eventually runs out. Which law is that, first or second? Second, okay? Energy flows from high energy to low energy. The energy is flowing away from the bouncing ball and into the surroundings. Okay, a metal spoon eventually becomes hot when placed in a pot of boiling water. Second law as well, okay? If the water is hotter than the spoon, the energy flows from the water to the spoon. All right, energy cannot be created or destroyed. That's pretty easy. Which law? First law. All right. What's the difference between a heat engine and a heat pump? Okay, one of them, they both are affected essentially by the second law of thermodynamics. One obeys and one gets around. All right. The heat engine obeys the second law of thermodynamics. It harnesses the fact that heat wants to go from hot to cold. Sorry, thermal energy wants to go from hot to cold. Right? If we put something in the middle, the matter that goes with the energy as it flows from hot to cold can do useful work. All right, so that's the heat engine. The heat pump, on the other hand, uses energy to move heat the opposite direction. It takes heat from our thermal energy, from a hot area to a cold area. Okay, and it usually has to do some conversions of energy in between there in order for that to work. All right, so one of them uses energy, and the other essentially just harnesses a natural process. All right, example of each: heat engine, prime example. Jet engine, heat pump, air conditioner, refrigerator. No. Okay, what is a perpetual motion machine? Okay, yeah, it's a machine that never stops moving because it doesn't require any input of energy. It also means that it converts all energy at what rate? Right, at 100% efficiency. That's impossible. Okay, but that's what a perpetual motion would theoretically do. A perpetual motion machine would theoretically do that. Okay, second law of thermodynamics we've said about 3 or 4 times already, okay, is that heat flows or energy flows from high energy objects and systems to lower energy objects and systems. Okay, number 8. 2 sticks are rubbed together and ignite. Okay, is the work being done on the sticks positive or negative? Right, it's positive for the sticks. They gain energy. Okay, it's negative for me who's moving the sticks. Okay, I'm using energy to move the sticks. I'm losing it because I'm giving it to the sticks. That becomes heat because of the friction between the sticks. All right, so it's positive for the sticks. It's negative for me. All right, water is observed to condense on the outside of a cold glass. Which way is heat flowing? Okay, water condenses because it essentially reaches its, condensation point and goes from gas to liquid. Okay, why do we see that happening on the side of a glass? Right, okay, because not the oxygen, but the water vapor in the air, okay, goes towards the glass, which is cold. The air is comparatively warm, okay, and as a result, the water vapor loses energy to where? To the glass. And then when it loses energy to the glass, it condenses and becomes a liquid, okay, and energy goes from the air into the glass, right? Okay, so energy is flowing from the air to the glass, and condensation is evidence of that. All right, which law of thermodynamics best describes the following statements? You can't get something for nothing. Right, energy is not created or destroyed. In this case, it's the first law of thermodynamics. You can't get something for nothing means you simply can't make something happen without putting energy in. Okay? B, you can't even get close to getting something for nothing. Still first law? Actually, it's both. Yes, it's first law, but the reason you can't get close is because anytime you try to get something to go, you lose some energy to the surroundings. Anytime you try and transfer energy to something else, energy is lost to the surroundings. Okay, C, a rock will never suddenly jump into the air. Okay. Right, you would have to give it potential energy. If I just leave the rock, it's not going to jump into the air because of which law? The first law. If for it to jump in the air, it would have to create energy. Okay, and a rock is not going to do that. All right, everyone with me on that one? Okay, number 11. This is the Homer Simpson refrigerator air conditioner trick. Okay, if you ever saw the episode where he wanted to get an air conditioner but he couldn't afford it, so what he did is he put a blanket over the refrigerator and opened the door and sat in there. Why doesn't that work? Where's the refrigerator trying to pump the heat? Out. If you put a blanket over it or just leave the door open, it's trying to cool the whole room, and it's pumping the heat into the area it's trying to cool. It can never catch up, and the condenser will fail. Okay? All right. Study hard for your test tonight. Be ready for tomorrow.